So Abdalla is from the Technical University of Munich. He started my PhD with me. He stays in Munich now. He's at Gerd Krammer's chair, and that's some joint work. You will see it. He will talk today about identification under semantic effective secrecy constraints, and he will tell you what.
How can I point?
The upper
the-
and longer. Press it longer. Yes.
That one. Okay. Hello everyone. So this is a work was done with Johannes, Roberto Ferraro, who was a postdoc in our chair, and Christian, who was in our chair, and right now here, Bolat Bash in Arizona, and Uzi Pereg, who was a postdoc in TU Munich, and then joined Technion. So basically, almost all of you right now knows about identification. So I just say a few words that identification can be enormously beneficial because of the double exponential scaling that we have as compared to transmission. And it can like basically explode the communication rates potentially. And we also are interested in a concept called semantic effective secrecy, which combines both secrecy, more or less standard secrecy criteria with stealth communication. And the work also interestingly touches upon like challenging technical issues, like from an information theoretic perspective, like how to deal with certain converses under certain criteria, under certain constraints sets, dealing with auxiliary random variables under identification, like dealing with some more or less examples that we will see, or see like a couple of them among multiple ones that we have dealt with. In the intermediate steps, actually, we like proved more or less an interesting result, which is actually was motivated by our work in identification, but the work is that result is not entirely tied to identification. This is the basic simple model that we have. We have Alice, Bob, and the eavesdropper, which we call Willy, just to distinguish it somehow from the usual Eve, which is just about secrecy. Here we have secrecy plus stealth, and we will see how they are defined. So basically, we have one message, we have one encoded sequence, XN, which is sent over a channel, and basically we have two marginal channels, one to the identifier. So some people actually call it decoder, but from the very beginning of identification, like 30 years ago or something like that, by Alsveda, he was actually, or even before Alsveda, some people call it liberally somehow decoding or decoder, but some others like prefer to call it other names, as Casper was saying. What name you called it? Verifier, yeah. And I called it the identifier, which is basically the same thing. And we have a message, and our goal is just to know whether the particular message has been sent at Bob, and if he shouldn't know two basic things. He shouldn't know any relevant information about M, given that he has received the ZN, and he shouldn't know actually whether any particular meaningful communication is taking place or not. So this is the additional stealth criteria. It's not only secrecy, which is the statistical independence between the message and the received sequence. It's also about that you don't even know whether a particular meaningful communication is taking place or not. So somehow this is more or less like formal description. I will just point out to some basic things. Here we have stochastic encoder. We are not dealing with deterministic identification as was dealt in the previous two talks. And actually, I don't think that it's possible to think about secrecy in identification without having stochastic encoder, without having randomization at the encoder. I just point out to the way that we are defining these deterministic identifier functions. Okay, so basically you have this deterministic identifier function at Bob. It has an input, which is yn, the received sequence, and it has also one message, one particular message among the identifier message set, which is interested in at a particular moment. Okay, and what it outputs is basically just a yes or no, a yes or no, or a 0 or 1. 0, which corresponds to no, that the message that I'm interested in is not the message that has been sent, and I'm not interested actually in knowing which message has been sent at all. While 1 means that yes, the message that I'm interested in at the current moment is the one that has been sent. And we have the two usual, more or less, errors. One of them is about whether I'm making an error. I'm saying that the message that I'm interested in has not been sent, but it actually has been sent, and this corresponds to 1. And what corresponds to 2 is actually that I'm saying yes, I'm giving 1 at the output, but for a wrong message. So actually, a certain M has been sent, but I'm saying yes, while I'm currently actually interested in another message, which is called M dash or M prime here. And in addition to this particular like requirements, I'm also interested in an additional thing. The additional thing, which is highlighted by 3, is basically the secrecy, the semantic effective secrecy criteria. Right now, it looks a little bit abstract, and I will just say something, and it will be like more clear, I think, in the next step, in the next slide. So basically, I'm interested in that the KL divergence between some reference distribution, which is QZN, this reference distribution is something that corresponds to a non-meaningful communication or the complete absence of communication. So it's some kind of reference distribution that's being the norm somehow at Willy side when there is actually no communication taking place. And this notation of EM and the circle of then W of Y given X n times, it's basically product, I mean. Basically, this is just the output distribution that's resultant of picking a certain input distribution, because this is a stochastic encoder, so there is a randomization. So I have a certain probability distribution that maps each particular message into one particular sequence with a certain probability. So it's not a deterministic encoder. Okay, and basically I'm picking that one of them randomly, one of the sequences that corresponds to the message, and I'm just sending it over the channel W of Y given Xn. So it's basically just the output distribution. Okay, the output distribution when there is communication taking place, choosing a message and sending it over channel in an IID manner. Okay, and just another thing to be highlighted is, another thing to be highlighted is just that the rate is actually 1 over n, the block length, log. So we have log the size of the message set. So basically, this corresponds to the double exponential size of the message set, basically, which is the very attractive feature in identification potentially. Okay, and then the usual thing is just that we are interested in the secrecy capacity, effective secrecy capacity for identification under certain conditions, that all of the errors asymptotically, I mean, all of the error bounds asymptotically vanishes in some sense. Okay, so basically the intuition about the effective secrecy measure, basically we start with the strong secrecy, not semantic one, and the strong secrecy, strong effective secrecy criteria is basically just a summation, just summing two criteria or two measures. One of them is actually corresponding to strong secrecy, and the other one is corresponding to stealth. Okay, and actually, the first one is just a mutual information criteria. So it's just the leakage, which is the mutual information between M and Zn, just more or less standard. And the second one, the delta, is the KL divergence between PZN, which is the output distribution, the reference, the output distribution, sorry, when there is communication taking place. Basically, that one, EM circ W of Y given X N, the one that we talked about, and basically the KL divergence between that distribution and the reference distribution. Okay, and using very simple chain rules for KL divergence, I think I should have expanded it. It would have been like clearer in one step at least. By just like having applying very simple rules for KL divergence, we are having basically the expectation over the message set, over the message distribution, sorry, PM, and we have inside the expectation the KL divergence between PZN given M, which is the conditional distribution of the output at Willy, given the message, okay, and QZN. And QZN here, this is in principle, but in our work, we are considering the case where QZN is just an IID distribution, which corresponds to that we have a reference distribution, but each symbol of that sequence that the standard that corresponds to some standard behavior at Willy is basically coming from one distribution, and that distribution is producing the sequence in IID manner. So they are uncorrelated or independent from each other, the symbols. This is in our assumption. So how to strengthen that criteria? Strengthening it by just considering the worst case. And this corresponds to the semantic notion of effective secrecy. So in this case, we are just considering the worst case probability distribution for the messages, which is actually corresponding, we can actually show it also in a few steps, that we are considering the KL divergence between PZN given M, the output distribution, given a particular message, okay, and the reference distribution, QZN, and we are considering the worst case message, okay? So it's two equivalent ways to see the problem, and the advantage, more or less, of the second definition is that we have already removed the expectation somehow, okay? So it's about either keeping the expectation operator and maximizing over the distributions, or entirely erasing the expectation operator and just maximizing over the message set. Okay, so one of the things we talked about right now is stealth. And stealth is basically, can be viewed, at least from an information theoretic perspective, as a simulation problem. What kind of a simulation problem? Not a simulation like a computer simulation. Simulation means like trying to simulate a behavior, which is like what we do, for example, in Monte Carlo methods or Monte Carlo simulations. We are trying to emulate some probability distribution, for example, by using very large sample and averaging for a certain number of times, and probably applying the laws of large law of large numbers or CLT or these kind of asymptotic assumptions under certain conditions. So here what we want to simulate is basically a distribution, a behavior, okay? So actually, the distribution here that we want to emulate, or the behavior that we want to emulate, we want to send something, okay, according to some probability distribution at the input, and we want to emulate the reference behavior at Willy, basically, and all of the same time, we want Bob to be able to decode a message. So in our case, we want two simultaneous tasks, basically. We want to simulate a behavior at one party, and we want to send a message to another party. So in this simulation tasks, one of the most basic of them, or probably the most basic of them, is called the simple. It's called approximation of output statistics, which is like self-explanatory somehow. The name. We would like to see what's the least amount of uniform randomness. So basically, we are using, for example, a uniform codebook in the communication or transmission case in order to simulate, and we just pick one of those sequences that are distributed uniformly and sends it over the channel, and we see what's the behavior at one party, probably one party or probably others. In the least or the easiest scenario, we have only one party, and we want to simulate that behavior basically. And that behavior here also is modeled as we have seen, just a certain reference output distribution. Okay, so what was shown by Verdu and Han, and I think other people collaborated like 30 years ago in this kind of problems, that actually the least amount that the optimal rate, basically, given that you have one channel, which is called W of y given x. So here we have only one channel. And given that you have one reference distribution that you want to emulate, it's basically corresponding to the min. Okay, so this is also more or less more similar to what we get in compression or source coding problems, that we got a min or a max because we are interested in the least amount of uniform input randomness. Okay, and here basically it means this result would tell you what would be the size of the codebook. So basically the size of the codebook, which is a uniform codebook that you could use, is basically 2 to the power of this expression. Okay, and this expression is basically you have a certain constraint in the minimization here. So you are not only searching for a certain px in the simplex that's defined here, you are restricted by using a certain distribution that satisfies this property, that the reference behavior, which is qy, basically has to be equal the input distribution that you are using after passing it over the channel. So basically, you are producing, using this uniform codebook, some distribution, and that distribution has to satisfy a certain constraint, that you are constrained in the distribution that you have to use in the input, and also you are constrained by the size of the codebook. So the size of the codebook basically has to exceed that size. Okay, so you cannot emulate basically the behavior or approximate the output statistics unless you at least have 2 to the power of that size of the codebook, 2 to the power of that value to be the size of the codebook. Okay, and basically what's not written here explicitly is that the criteria is either a variational distance or a KL divergence, and some people use it some people use that because each one of them has its own advantages. Okay, the results that we got as an intermediate step, actually, which doesn't have particular relevance to identification or particular, doesn't have to be related to identification in some way, that what if we want to have 2 concurrent goals? One of the goals is basically to emulate or simulate a behavior at one of the 2 parties, which is receiving the output z or zn, the sequence, and we want to communicate in transmission. So it's not identification; it's just the usual more or less communication behavior over a certain channel, which is W of y given x. So W of y given x, the party that receives y is basically interested in in decoding, and the other one that receives z is actually interested in is not interested in. You just want it, basically. You want to emulate a certain standard behavior at it, such that it doesn't recognize whether you are actually sending something from the codebook or not. Okay. But here you will have actually a maximization, because here it's basically we are searching or looking to find what's the maximum communication rate, okay, such that the simulation behavior is being satisfied at the other party, okay? So you have a maximization over the mutual information between X and Y, as you usually have in Shannon problems. But on the other hand, we have a restricted set. And this restricted set is actually having another additional criteria or additional, restriction. And that restriction is that basically we are searching for a certain PX such that we are restricted in the PX that we can use, such that the output distribution during communication would be equal to the reference distribution. And we are having another constraint, which is that for this particular PX, the mutual information between X and Y has to be larger than the mutual information between X and Z. The mutual information between X and the random variable received by the decoding party has to be larger than the mutual information between X and Z, the random variable received by the simulation party, more or less. Okay, how can we show like some curious example of this? We just want to show something. We are showing a class of channels which are called degenerate channels. What's meant by degenerate channels? We'll see it. Basically, for many problems, many of the normal channels that we know, the usual channels, like the binary symmetric channel, if you are given a certain probability distribution, if you are given a certain QZ that you have to emulate, basically you have only one PX that you can use, okay? So basically, for a binary erasure channel or binary symmetric channel, there is no ambiguity about which probability, there is no there is no basically maximization problem, there is no optimization, because given a certain QZ that you have to satisfy, if it's a binary symmetric channel, there is only one possible input distribution, okay? So there is no optimization in some sense. It's actually simpler than that. So for degenerate channels, it's actually that for a given particular output distribution, there is more than one input distribution that could satisfy the property that we are talking about. So actually, there is an optimization problem, and you have to think about which PX that you have to use, okay? Which is not in the usual, more or less standard channels that we talked about. So this is a very particular and very peculiar channel, and many people uses it in papers just to demonstrate a certain point. So for example, just imagine that if epsilon is equal to 0 here, basically you would have 1, 0, half and half, and 0 and 1. So basically, this is what? This is a binary symmetric channel. This is a noiseless channel, okay? That you send a 0 and receive a 0, and send a 1 and receive a 1, okay? And then you have an additional input symbol, basically, which I call it erasure. It's not really an erasure. You can think of it as an inversion of the erasure channel, more or less. Why? Because basically you have a symbol that you have an equal probability that that symbol, that additional symbol and the input would go to either 0 or 1, okay? So if you are thinking in terms of communication, I'm just demonstrating right now the rather straightforward case of epsilon equal to 0. Would it make sense to use the second input symbol? No, right? Because it would be just utter confusion, right? A symbol that actually goes with equal probability to 0 and 1, so you wouldn't be using it, and you would just use the normal channels. So the probability input distribution, the optimal input distribution, would be half and half on the 0 and on the 1, okay? So just uniform distribution. It's not really uniform because it's half and half. I mean, uniform after excluding the useless symbol somehow. And on the other hand, you will get a capacity of 1, right? because you are sending basically noiselessly if you have an epsilon of 0. This is what I'm saying. Okay? So we are considering this case actually if epsilon doesn't have to be 0, just any number between 0 and 1. And one of the cases for sure would be 0. So we would like to contrast how would be the behavior of this optimal approximation of output statistics rate as compared to the capacity of the task that combines both transmission, usual communication, plus approximation of output statistics. So basically, this is the curve that we get, which is looking somehow cool. So basically, you have the blue line, which is just the usual transmission rate. Okay, and this is basically for the case, I think epsilon equal to 0.1. So basically, the blue case is just the same as the probability distribution, the capacity of binary symmetric channel with a flipping probability of 0.1. Okay, and what do you have here in the horizontal axis? Basically, you have all of the possible Qs, the possible. Did I define Q here? Q, which is equal to QZ of 1. Okay. Basically, you have two input symbols. So you have QZ of 1 plus QZ of 0 has to be equal to 1. Okay. So you just represent the reference output distribution with the number of Q, with the number Q, right? This is sufficient for this case. So as we are sweeping actually the Q from 0 to 1, we see that for a particular epsilon, which is 0.1 here, there is actually a range of values here between 0.9 and 1, and here between 0 and 0.1, which is actually between 0 and epsilon, and between 1 minus epsilon and 1. You cannot actually simulate that behavior given the channels that we have. Okay, we are actually assuming two identical channels. Okay, they are not the same statistically for sure, but I mean the distributions are the same between WZ given X and W of Y given X. Okay, and we see that actually for the combining the transmission and approximation of output statistics behavior, we have more or less, let's consider the case where Q is equal to 0.5. You just have a uniform distribution to be the reference distribution that you want to simulate. Basically, you reach the point where you are just using the uniform distribution among the 0 and 1 and setting the erasure to 0. And then it touches upon the blue line, okay, the usual transmission capacity for a binary symmetric channel. While actually, at this particular point, which is 0.5, you can just do a very dumb thing and very intelligent thing in some way that you can just use in order to simulate the uniform distribution at the output. You can just use the erasure symbol at the input and just use it all the time. And basically, it does without any communication. It does. It simulates the uniform behavior at the output. Okay, and so when you are thinking in terms of optimal rate for approximation of output statistics, which is modeled subsequently as stealth, basically you are thinking of the least amount of randomness, the least amount of uniform randomness. And the least amount of uniform randomness at this point is basically just use the same symbol all the time. And that symbol is actually, because of the peculiarities of the channel, it just interchanged between the 0 and 1 at the output. Okay. While if you are interested in both simulating the behavior and actually sending useful communication, and you are thinking of the maximal rate of sending communication, then basically you are going to the binary symmetric channel. This is at the 0.5 when you are just simulating the uniform distribution at the output. In the meantime, basically you are affected by Q. I didn't try the expression. I'm just putting the plot here. You are actually having a dwindling rate somehow, dwindling capacity that does both of the two tasks until it reaches 0, and it's symmetric around 0.5. Okay, and for the approximation of output statistics alone, it's actually It's also symmetric, but symmetric around 0.5. And it gives you this peculiar shape that actually it's a 0 here, it's a 0 here, and the maximum is between somewhere in the middle between 0.5 and the 0.9, which is 1 minus epsilon. Okay? And you have a symmetry between the two behaviors. Okay, so this is just like an interlude for people who might be interested in these kind of things. Even if they are not interested in like identification in its own. So basically, the idea that we have, why we were interested in this previous scenario, we're interested in that being able to produce an ESID code, which is effective secrecy identification code, using a code, using basically two codes. The first code is an approximation of output statistics code, transmission code, basically, and another second part, which is effective secrecy transmission code. Why? Basically, effective secrecy transmission is just effective secrecy, but in the communication setting, not in the identification setting. We want to use a hashing lemma, not hazing lemma. So this hashing lemma basically tells you, I just tell you the intuition about it, that basically if you have a certain code and you a certain approximation of output statistics code, okay, you just randomly as the encoder choose any M1, okay, and you have a particular M in your mind that you want to send, okay, and the universal, the hash, the epsilon almost universal hash function, basically, and this lemma tells you that given a certain message that you want to send that belongs to the set M, okay, just choose any M1, which belongs to a certain approximation of output statistics code, okay, and you would have a family of functions basically that maps into another M2, like another message space somehow, and the strategy is basically that you send, you are interested in M at the encoder, you want to send it, you just looking at M1, choose any of the M1s randomly, okay, and then basically the choice of M and M1 would determine what would be M2 that you have to send in the second part of the code, okay? And the strategy is that the second part of the code doesn't have to be very long in the block length, and at the identifier side, basically he decodes M1 because he has the code book for the approximation of output statistics transmission code, and then he's interested in a certain M. He knows what he interested in. So the very basic property of the hash, almost universal hash function, is tells you that the second identification error, which is about confusing two messages, basically one that you have sent at the encoder and the one that you are interested in, and saying that it was not sent, by then the collision between the two messages basically for the decoder would almost cease to exist, or would be like very small somehow. Okay, and like I erased like some like more detailed description of the thing, but more or less this is the I try to convey an intuition about it. So basically we have a corollary here, that the capacity for effective secrecy identification code, okay, which is a function of the two channels, the one to Bob and the one to Willie, is basically equal to, and a certain QZ, which is the reference distribution, is equal to the mutual information between X and Y. Okay, just the mutual information between X and Y, but actually you have also a certain constraint on the on the probability simplex that you are searching for px in. Okay, and that criteria would be that px, the output distribution, basically when you are doing the communication, has to be equivalent to the reference distribution. But what's actually a more capable channels? More capable channels is just a channel where it's always, for any px that you choose, you are always guaranteed that the mutual information between x and y is larger than the mutual information between x and z. So you have two marginal channels, and you are guaranteed that for a marginal channel, for any particular choice of px, the mutual information is always larger than the other one. Okay, but actually, the more capable channels are somehow restricted set of channels. Was it easy to actually have a capacity theorem for the more general channels, which doesn't satisfy this property? Unfortunately, it was not the case. So basically, we have two bounds, an upper bound and a lower bound. Okay. But before going to the upper and lower bound, we just illustrate a simple example of more capable channels. What if you have the two marginal channels, to Bob and Willie, two binary symmetric channels, and you have absolute statistical superiority of one of them compared to the other. And this is just corresponds to the case where epsilon 1 is smaller than epsilon 2, okay, by two binary symmetric channels, and epsilon 1 is epsilon 2. So are always guaranteed that the mutual information between x and y would be larger than the mutual information between x and z, okay? And in this case, basically, we would get this particular expression for this example, that it would be equal to the binary entropy, both of the capacities that we have dealt with, would be equal to the binary entropy of P star epsilon 2 minus the binary entropy of epsilon 1. This one should be a binary entropy, okay? And the star operator is defined in the usual way for people who are familiar with information theory, and the P star epsilon 2 has to be equal to Q, which is corresponding to QZ of 1. How this would look like, basically, we can just talk about the green curve, and the green curve is basically is more or less similar to the COST behavior that we have seen before in the degenerate channels. So basically, with varying Q, you have a peak when the output distribution, the reference output distribution, is equal to is a uniform distribution. Okay, then basically you are touching upon the usual capacity without any simulation behavior or stealth behavior. Okay, and other than that, you are declining till you reach a point where actually you are unable to emulate the behavior, emulate the reference behavior. And this is the case here when you have 0.9 till 1, and 0.9 is corresponding to 1 minus epsilon, and you have symmetry between 0 and 1. Okay. But what if the channel is not more capable? Then, as I told you, unfortunately, we don't have a general capacity expression, but we have two upper bounds, one upper bound, sorry, and one lower bound. Okay, I can go to the example, then go back to the result just to illustrate the point. Because other than that, the result will be a little bit esoteric. So basically what, here I'm just showing a channel which is, it's very difficult to show, basically, or to ascertain which channel is better than the other. In the previous case, if you have two binary symmetric channel, then with just considering the flipping probabilities, I can say that the channel from Alice to Bob is certainly better than the channel to Alice and Willie, or the other way around. Here, it's not the case. It's also very dependent on epsilon, the value of epsilon. Why? The channel that we have here is basically, we have Alice, and Alice is here. Here, this is like an additional block that we will talk about. And we have Willie and Bob is actually receiving two symbols at a time. So X1 is being sent over an erasure channel with a parameter of epsilon, and then Y1 is being received at Bob, and the same for X2. Okay, so actually you have a vector observations in some sense. Okay, but Willy is basically having only one channel, only one sub-channel. So here you can say that Bob has two sub-channels, which is composing the channel itself, and Willy is having only one channel, but that channel is actually noiseless, which is a hugely can be a huge advantage for sure. So just consider the case. What if epsilon is basically equal to 0.1? Then basically, if you are just using the results that we know for the binary erasure channel and doing uniform distribution without having to think right now about any simulation behavior, then basically I can send 1 minus 0.1, right? Because the binary erasure capacity is 1 minus epsilon. So I can send 0.9 bits to the first over the first sub channel to Bob, and another 0.9 over the second sub channel to Bob, right? So basically you would have 1.8, right? Bits, the capacity between Alice and Bob. This is in the case of epsilon equal to 0.1. And what's the best thing that you can do? Is just to send 1 bit, right? And this is a good thing for sure. But compared to Bob, then Bob is absolutely having an absolutely like better channel. But what if epsilon is equal to 0.8, for example? Then basically you have 1 minus 0.8 and 1 minus 0.8, right? So you have 0.2 plus 0.2, then you have 0.4 bits, okay? While Willy is having what? Is having 1 bit, okay? So in this case, actually the channel between Alice and Willy is better, demonstrably, like clearly better than the channel to Alice and Bob, okay? So in this kind of scenario, we can talk like a little bit like formally about it and all that, but just for now, here it's always dependent on the epsilon, okay? On saying whether the channel to Alice and Bob, to Alice, from Alice to Bob is better than the channel to Alice and Willy or not, which is not the case in the binary symmetric channel, for example. Okay, so for these kind of channels, so if epsilon is smaller than 0.5, basically we have the upper and the lower bounds to be coinciding, and we would have this kind of simulation behavior. So we'd have the capacity of the capacity of the ESID, the effective secrecy identification capacity, would basically take again this kind of bell shape, and the maximum would be more or less in the center, okay? But actually, because of the peculiarity in the binary erasure channel, the good thing here compared to the binary symmetric channel is that we can simulate the whole range of Qs from 0 to 1, okay? So in the case of epsilon smaller than 0.5, basically we have capacity and we have somehow clear behavior. The thing that if we have epsilon smaller than larger than 0.5, the case here is epsilon equal to 0.8, for example, we have more muddy behavior somehow. And I will just demonstrate it and go back to the bounds and talk about it, and then it's finished. So basically, we have two lower bounds. A lower bound, which is corresponds to the red curve, and we have another lower bound, which corresponds to the black curve. And we have an upper bound, which corresponds to the blue curve. So so we have light blue and, okay. So basically, we have two cases for the lower bounds. The thing about this particular channel is that basically, if you don't do randomization, and this is basically this block, if you don't do randomization over the channel, and you have a binary erasure channel with parameter like larger than 0.5, then basically you can never have you can never have like to satisfy the two conditions, or you can satisfy the two conditions of both communication, basically, and in this case identification, and simulation, in this case interpreted as stealth, but for very limited range of queues. Okay, so if you want to like have a larger range of queues where you can do the two tasks, okay, because as we know from the basic wiretap channels, that more or less you are expecting statistical advantage for the first channel to the legitimate user as compared to the eavesdropper, okay? And you have to do randomization if the statistical advantage is not visibly there in order to create the advantage, in order to have positive secrecy rate. So the case here is basically corresponding to that. If you don't do any randomization, then you have the whole range here a zero rate. A zero rate where basically you can do the simulation, but you can't do the communication, okay? So you can have a zero rate where basically you cannot simultaneously satisfy the two conditions at the same time, having a positive rate and simulating the stealth part as well, okay? But if you are using randomization, then basically you can allow for some positive rate while satisfying at the same time the stealth constraint, okay? But on the other hand, we have this upper bound, and that upper bound does not match even the inner bound that we have with the randomization, okay, which corresponds to the black line here, okay. So what we can infer here from information theoretic perspective, just the mechanisms or the machinery that we are using, randomization most probably means introducing an auxiliary random variable, okay. So this is like touches upon the fundamental, one of the fundamental like challenges in potentially many identification problems, that it's very difficult to deal with auxiliary random variables in converses for identification. So I'm going back right now to the expressions. Okay, so this is basically the inner bound that corresponds to the lower bound that we have if we don't allow randomization. So here we have everything in terms of x, the input, okay? And we are not using any auxiliary random variable like u or whatever, okay? And we are seeking to satisfy the two conditions that we have shown before, that the mutual information between x and y has to be larger than the mutual information between x and z, and the simulation condition, okay? So, and we say that the capacity has to be larger than the maximum of this mutual information under this probability simplex. So here it's a lower bound, an achievable rate, but without allowing any randomization. What if we allow randomization? Then basically we have to introduce this auxiliary random variable u, and we have to introduce this Markov chain property that u and y and z, the outputs, has to be conditionally independent from each other given x, and we have the similar mutual information condition, but with u, not x. Okay, and this basically is just an extension for the previous property with like with allowing for randomization. Okay, so this is a potentially improved lower bound compared to the previous one. But the problem that we have is basically, yeah, that the upper bound itself, okay, we have the same probability simplex constraint on the optimization problem, but we have the mutual information between x and y, not the mutual information between u and y in the if we allow randomization. And given the data processing inequality that we know from basic information theory, this is decidedly higher decidedly higher than that quality, given that we are optimizing on the same set. Okay, if the two like probability simplex sets that we are basically optimizing over are different, then data processing inequality does not necessarily hold. But given that we are optimizing over the same set, the data processing inequality has to be satisfied, and the upper bound is strictly higher than that bound. Okay, so basically, it was very tricky to deal with this somehow, with how to introduce auxiliary random variable, which is corresponding to randomization in the outer bound, and we didn't manage to get general general capacity theorem somehow. So it was only a capacity theorem for the particular cases where you have, for example, more capable channels. So the challenge is that new converse proof techniques are needed, probably in identification, or probably would never be able to be met. We don't know. And we touched upon simulation of over channels combined with communication in general, which doesn't have to be tied to identification, and about the practicality of the schemes and all that, which is the usual question in such things. Thanks.
Yes, thank you.